Hey, hi. Actually, we looked at neural networks and we have compared it with brain and how there is similarity between brain and neural networks. But our the main intent was to explain uh, how people have come up with a concept called neural networks and how really it worked out pretty well. Um, and we also looked at the equations on how the equations would work. But today we will go through the equations of neural networks. We'll also try to look at different kind of optimizers for neural networks. We'll look at regularization, how regularization is done here, and we'll also look at hyperparameters that are there for neural network, which hyperparameter tuning, how do we do it and stuff. So we'll just mostly we'll ask ChatGPT and then we'll do how we want to do it. Mm, I think that's it. We will decently cover neural networks if we have all these concepts covered. So that should do. Okay, let's get started. Let me share my screen. Let's go to ChatGPT and I'll start asking questions. Sorry. Mhm. Let's go this. Okay. So let's look at the overall equations, right? So let's look at some simple neural network. Actually, neural network. Yeah, so this playground is pretty interesting. So visually, we can actually see how the overall neural network would work and all that stuff. So see, we can play around. Let's say the two and so next here layers. Neuron's output is two. Then okay, we show test data classification, volume classification. Noise, bad size. Ratio of training to test data 50%. Okay. Batch size 10. We'll look at all this. These will be part of Hypermodel, but I want to show you how these neural networks will look like. So X1, X2, if there are two features, if you're giving it to two neurons and outputs are expected are two outputs. Okay. So we can also reduce one and then we are classifying only the one that is there. Let's take this scenario where we have uh, two x1 x2 inputs, two neurons in between and this. So let's try to look at this on what happens here, right? So let's go here and then see. mm, so I said each neuron has two parts. One is the linear regression equation z, and then there is an activation equation, right? So linear regression. Yeah, so it's something like this, right? Like okay, so we take this down equation. W1, W2 weights, B1 bias, X1, X2 features. I think I can type it faster than this. Yeah, so this is the equation, right? So G, okay. Z of Z. So it will be like this. If we take ReLU activation function, Z of Z will be like this. So Z is W1 X1 W2 X2 plus B. Z is equal to, oops. So Z is equal to this equation, and to that equation we apply, sorry, when I say, let me set Z. Z is equal to W1 X1 plus B, and we apply Z of Z, that is max of 0 comma is ReLU function. This Z is activation function, and activation function can be multiple. So what are all the activation functions used in neural networks? So sigmoid function 1 by 1 plus e power minus z, which is used in logistic regression. Hyperbolic tangent function, this is tan h, and rectified linear unit ReLU, um, that is max of 0 comma z. Leaky ReLU is where it doesn't really become zero, but will pick up a small alpha in a way that so he's saying z greater than 0 is z, okay. So now we are talking about negative values, that is z less than 0. For z less than 0, instead of making it 0 completely, we will actually multiply it with alpha, where alpha is um, will help, alpha will help making the value little more than 0. So similar to ReLU, but allows a small positive gradient for negative inputs, helps alternative, help elevate the dying ReLU problem where neurons can become inactive. Yeah. So parametric ReLU, similar to leaky ReLU, but allows the slope of the negative part to be learned during training. I don't know what is difference between leaky ReLU and parametric ReLU. Exponential linear unit, I don't know what to do, but as a smoother transition for negative inputs helps. Right? Okay, softmax function. So softmax function is e power z of a specific value divided by sum of e power z's, that is softmax. Okay. Used in the output layer of multi-class classification problem. Outputs a probability distribution over k classes where some of the probabilities are equal to 1. Oh, is it so? Okay, I didn't know that. So if I want softmax function, if I have three classes. If I do E of z1 by E of z1 plus E of z2, E power z2 plus E power z3, then yeah, dividing by sum of the particular numbers will actually give you the rough distributed value. Just thinking 2, 3, 4, 2 by 9, 3 by 9, and 4 by 9 will actually give you values which are distributed across these three ranges, correct? Yeah. So that's right. Hmm. So these are all the activation functions that are brought. But I think the list is much more than this. Let's look at online of activation functions in neural networks. See activation function, softflex, sigmoid, exponential function being repeated. 13 more. What is activation? It is thing function that you use to get put off. It is also known as transfer function. Okay, yes or no, if maps the resulting values in between 0 and 1 or minus 1 to 1, etc., depending upon the function. There are two types: linear activation function and non-linear activation function. Okay. Linear identity activation function, as you can see, the function is line or linear, therefore the output of the function will non-linear activation function. Most used activation functions non-linear helps. The graph looks like something like this. Easy for the model to generalize or adapt with variety of data and to differentiate. Sorry. Non-linear activation functions are mainly divided on the basis of their sigmoid or logistic 1 by 1 plus e power minus z. We use sigmoid function is because it exists between 0 and 0 to 1. Therefore, it is especially used for models where we have to predict the probability as an output. The probability of the anything exists only between 0 and 1. Sigmoid is the right choice. Okay. Principle. Again, for the sigmoid. Um, Large sigmoid function can you? The softmax function is a more generalized logistic activation. Oh, oh. Okay. Tan h is also like as a logistic sigmoid, but better. The range of the tan h function is from minus 1 to 1. Sigmoid 0 to 1, tan h వచ్చేసి minus 1 to 1, and it's as shaped. Okay. The inputs will be mapped strongly native and the zero inputs. We have 0 and tan h graph is differentiable. The function is monotonic, while its derivative is not monotonic. It is mainly used classification between two classes. Okay. Use activation function in the world right now since it is used in almost all the network circuit planning. Okay. And okay, but the issue is all the negative values become zero immediately, which decreases the ability of the model to fit or train from the data properly. That means any negative input given to the ReLU activation function turns the value into zero immediately in the graph. Then affects the resulting graph by not mapping the negative values appropriately. Okay. Leaky ReLU. It is attempt to solve the dying ReLU problem. Can you see the leak? So the leak helps to increase the range of ReLU function. Usually the value of A is 0.01 or so. When A is not 0.01, then it is called randomized ReLU. Okay, therefore the range of leaky ReLU is minus infinity to infinity. Both leaky and randomized ReLUs are monotonic in nature. Also, their derivatives are also monotonic in nature. Taking the curve to know in which direction and how much to change or update the curve depending upon the slope. That is why we use differentiation in almost every part of machine learning and deep learning. Yeah. In the backward propagation, we do differentiation in order to see how the parameter needs to be adjusted. So for that, we need functions which are differentiable, so that those gradient descent based calculations can be done effectively. That's all. So it's identity f of x is x, binary step 0 or 1, and then logistic 1 by 1 plus z, tan h is 2 by 1 plus e by 1 minus 2 c minus 1. Okay, I didn't. Something is wrong, is it? 2 minus 1 e power 2x by 1 plus e power minus 2x is also possible. But divided by is tan hx function. Okay, let's do it. 1 2 minus 1 1 1 minus e power minus 2x by 1 plus e power minus 2x. Yes, that should do. And if you bring it, it's e power 2x minus 1 by e power 2x plus 1. It's easy, no? Why to complicate it so much? Tan h of x. Yeah. Arc tan inverse of x. Hey, tan inverse, isn't it cot? Don't know. Okay, let's see. Um, Rectified linear unit, ReLU 0x. Parametric rectified linear unit, alpha x and x. Leaky ReLU and parametric ReLU is both are same, is it? Okay. Exponential linear unit, alpha into e power x minus 1. Every day is saying exception. Um, Soft plus logarithm of 1 plus e power x. We can look at the graphs. So Gaussian. Gaussian is something we have not covered in this. Gaussian will work like this. Okay. Means Gaussian will take negative as positive and positive as negative. Okay. I think in this graph he has not shown leaky, because if he shows leaky, then there will be a line below the negative uh, axis. So yeah, it's only sigmoid, tan h ReLU soft plus and Gaussian. Soft plus is going up. Remaining are going close to zero. Positive. ReLU also will go value here is shown as if it is going towards zero, but actually it is incremental. Okay, so that's with the activation functions. Now, um, let's take sigmoid function. If you take sigmoid function as activation function, then what happens? 1 by 1 plus e power minus z, sigmoid. This one, right? So if you take this one as activation function, now what happened? You take W1, W2. I think I can't do it on this one. I should take a paper and actually, you guys can't see it. I'm sorry, but let me do it here for understanding purpose. So if you have two neurons, what happens? One is so activation function is 1 plus 1 sigmoid. If you take sigmoid as activation function, 1 by 1 plus e power minus z, z is equal to w1 x1 plus w2 x2 plus b1. But this we have we have input x inputs one layer with two neurons and then output, right? So let's w's will be repeated. Each the three input will not have parameters will be there for three of these, right? Two neurons here and output layer has one neuron. So this will have to differentiate between them. Let's call it first, second, third neuron, right? So you'll make it 1 1 w12 and b11. Okay. Now what happens? This is for first one. Second neuron below is again the and we call it z11 z11. So 1 plus e power minus z to 1. Matter of fact, it is easy. Z1 is enough. 1 1 you need not call it. Okay. And here it is 2. Okay, ez2 and z2 is equal to w21 x1 plus w22 x2 plus b21, right? And then you have third one is 1 plus e minus z3. Third one is nothing but our output layer. That means if you look at this one, okay. I'm as he said, usually we use a softmax for output this thing so that it will help in classification of the problem. But we can use softmax also, not a big deal. Um, but we have anyways, we have only one, so we can actually have sigma also. Let's go with for having uniformity values. So w31 x1 plus w32 x2 plus b31. Okay, so these are three nodes that we have used. Now what we are saying, now third one is wrong because this first neuron's output we call it as a1. Second neuron's output, let's say a11. Second neuron's output we'll call as a21. Then in z3 it will become w31 a1 plus w32 a2 because x1 x2 is inputs to these two neurons. The output of this neuron is a1, output of neuron is a2. A1 a2 will be fed into this neuron. So this neuron z is calculated as w31 a1 w32 a2 plus b31, the base term for this particular neuron, right? So that is in turn calculated as 1 by 1 plus e power minus z minus z3, right? So first we'll put z3 is equal to W31. What is A1? A1 is nothing but 1 plus 1 e power minus Z1 plus W32 1 by 1 plus e power minus Z2 plus B31, right? So W31 by 1 plus 1 power e, this if I constitute Z here, 1 by 1 plus W1 x1 plus W11 x1 plus W12 x2 plus B11 plus W32 into 1 by 1 plus e power minus W21 x1 plus W22 x2 plus B21 plus B31. So Z3, if you look at it, it is actually internal function of x1 x2 itself. Only thing is we are putting it into multiple. So the x1 x2 that is coming here, we are putting them into two different sigmoid functions, and and that becomes 1 by 1 plus e power z1, 1 by 1 plus e power minus z2. These 1 plus 1 by 1 plus e power z1 is being carried here. So if you look at it, we are doing nothing but we are actually arriving at the final function, which is a complex or it's a weighted output of two different models. Let's imagine the two people who are standing here, like Raja and Suresh. So, Ramesh and Suresh. So, Ramesh, this is my model. This is correct. And Suresh says this is my model. And there is a third model who is like the final call. Whoever gives the final call, what he does is he doesn't want to be biased. He doesn't want to take anyone's direction. He feels that both of them are partially correct. So what it does is he takes a weighted average. That is, okay, I'll give W31 weightage to the first one and W32 weightage to second one. I'll take both of them. So he takes both of them, W31 and W32, and he will add his own bias B31 a little bit to it. So that will become this. Now, if you look at this whole logic, what happens when as you go incremental? So, like let's say you add one more layer like this. So, and bring one output. Now, what happens? A1, A2 is kept both here. So it becomes 1 plus, oh, sorry. So it will become W31, W31 doesn't matter. Okay. So W1, W2, W3, W4, W5. Let's think like that. So W3, sigma of W3 into A1, A2. Let's say this is not required. A1, A2. So sigma W into W3 into A1 output of this, and sigma W4 into A4 plus B term bias. Let's assume that bias is 0 for now, but so go with it, then what happens is this will become a is nothing but 1 plus e power minus z1 z2 here. Here what will happen, it will become 1 plus 1 by minus z3 z4, but z3 is equivalent to um, sorry, z3 is equivalent to w1 sorry, w3 a1 output of this are to give you pressure w31 a1 w31 a2, and that's what is 1 plus e power minus z, and here it will become w41 a1 w42 a2. Now these two layers, if it goes here, and output, if you consider a1 a2 a3 a4, this a3 a4 will be inputs to this, so it will become w3 1 plus 1 plus 1 by 1 by 1 plus e power minus z, where z4, say z1 z2 z3 z4 z5, then there z5 is equivalent to w w1 w2 w3 w4 w5 w5 of 1 plus e power minus c5, right? No, so it will become, this will become a3 a4, a3 is equivalent to z3, right? And plus w, yeah, phi 1 w phi 2 into 1 plus e power minus z 4. So multiples of this two, right? W weightage sum of these two outputs. Those outputs, in turn, if you look at it, those outputs z3 and z4 are actually weighted inputs, weighted sum of weighted outputs of these two. So it's like a chain. We are keeping it like 1 power e 1 by 1 plus e power, and then again w into 1 by 1 plus e power. So I'll put it here. So it's becoming w into 1 by 1 plus e power w into 1 by 1 plus e power w, and everything is minus w into 1 plus 1 by e power. So as the number of layers grow, the equation will keep growing, x plus b plus, okay, let's remove the b term for now. So it's something like this. So it will go incremental as w 1 by 1 plus e power minus w. In this power term itself, this is one term, 1 by 1 plus e power again. So what happens is, given w x weighted x parameter, we are actually applying the sigmoid multiple times with different weights. This is w5, w4, w3, w2. So like that, in this term itself, you'll have w1 x1 plus w 1 x2, something like that, right? So you will have multi layers that are being applied on a given x1 x2. They are applied with 1 plus sigmoid, and the output of them is put into another sigmoid. Output of those will be put into another weight sigmoid with weights. weighted sum of those output is put into other segment. So it's a by basing on number of loops, you will have number of powers to which this will grow. So it went to three layers. So end of the day, neural networks output, if you look at, this is your final output. So if you have, instead of doing all this, if you have one single equation like this, then your neural network is equivalent to this equation. That's the whole logic. So but what we are doing, instead of solving that particular one complex equation, we are actually dealing with multiple smaller, we are breaking down the whole problem of arriving at a complex equation into smaller parts, and those smaller parts were being computed separately, and those smaller parts are being given like this big one by multiple parts. We are breaking it down to smaller pieces. The smallest part is the last third term, right? So we are solving that third term. So if you look at it, this is layer 1, 2 nodes. This is layer 2, 2 nodes. And this is layer 3, 1 node, 1 neuron, 2 neurons, 1 neuron. So first we calculate the first layer, these 2 neurons output, and then we calculate this neuron, and then we calculate this third neuron. So like this, we calculate the whole sum. But if you calculation wise, if you look at it, this whole equation, if you calculate, you will get the output. So instead of during all these neural networks, if I have one equation like this, but here the assumption is activation function is sigmoid function. Provided the activation function is sigmoid function across all neurons, then this particular equation, one equation will give me, instead of running all these neural networks, blah blah blah, and all that stuff, I can remove it, and then I can go with this particular equation. I can solve this. Um, but such a complex equation, instead of solving it, we are breaking it down. Each piece we are separated it and then bought it as one layer. Like the top piece, first piece, layer 1, second level, layer 2, third level, layer 3. So we broke down the problem. So this is layer 1, layer 2, layer 3, and these three layers being conjugated together, the mathematical equation is broken down, and then we using these equations, we are actually solving them. Not only about forward propagation like this, where we apply mathematical equation on each of them separately, we are also seeing advantage of how to uh, so we start with one w1, w2, w3, w4, w5, right, as the parameters. Those parameters needs to be will be randomly picked at one point, and then uh, how do we increase the parameters, or how do we approach to the optimal values of this parameters is we use something optimizers there. In the optimizers, one we have seen already in regression is gradient descent, where you pick ww1, and then what you do, you do a grade to you do a gradient descent, so that till you reach your local optima. How do you do gradient descent is you do a w is equal to w, or w nu is equal to w old minus lambda into derivative d of loss function by d of cost function by dw. So you do a derivative of the cost function to, because I'm repeating all those things, but nothing wrong. You want the cost function to be reduced, so you derivative of cost function will give you direction in which it is going down, and you take a derivative, you multiply it with lambda, which is nothing but your learning rate, basing on that, which defines the steps in which the w will be, gradient descent will be done. So w minus lambda into, you use the derivative and you reduce it. So w1, w2, w3, w4, w4, w5, these four weights, we can reduce them basing on derivatives. And how do you calculate these derivatives um, for each of them? That is something we'll see as part of um, back propagation. So Anyways, so to start off, you understood that this is nothing but the whole neural networks is one single equation, which is broken down into smaller pieces, has to be calculated individually so that the computation is easier. And also, if you look at it, we'll also, from compute perspective, will take the advantage of um, running the whole calculation on one single thread. We'll split it. We can actually go parallel, and these two are independent, right? As long as x1, x2 is known, w1 of this and w2 weights of this are known, we can calculate them parallelly. So even if there are 20 layers here like this, even if you have multiple layers here, then all of them can be calculated in parallel, and then output of it, once you get it, again these all can be calculated in parallel, and then those can be given as input to this. So, and see features, we can add the features here, x square x. So uh, yeah, parallel processing is one advantage of breaking down into neural networks and stuff, and the individual weights can be calculated, also calculated separately at each layer. We'll look at how the weights parameter optimization will be done. So let's look. ChatGPT's outputs are not 100%. I don't like those outputs to accept. So because these topics are needs to be given in much more detail way. Let's look at online blog on what are different optimization techniques. Optimization. Okay. Optimization. Optimization import process in the training of neural networks. The goal of optimization is to find a set of parameters that yields the best performance for it. So whatever gradient descent that you do itself is optimizer. The optimization of parameters in order to have the least amount of cost, that is within the cost graph, we for given the parameters that is there, we want to pick up the least cost that is possible with. So you keep reducing the parameters, or uh, you keep uh, not reducing or increasing, whatever, you keep changing the parameters w1 w2 w3 w4 w5, um, until you reach the minimal cost for the overall function. Because here if you look at it, you look at the hidden layers as a black box. So x is input, y is output. So you, once y output comes and y original is there, you calculate the cost here. The intermediate outputs are not never compared with y, because that's not your objective. The objective is the output layer. So you calculate the cost of the output layer, and then you work backwards to find out how you can reduce the weights across all the layers in order to uh, reduce or change the weights across all the internal neurons, so that the y is closer to the expected y. Okay, so y predicted is closer to actual y, so the difference loss in between those values is minimal. That's our objective. So optimization, process of minimizing and maximizing mathematical expression. This process is used to reduce losses and provide the most accurate results possible. Okay, this is optimization. So let's look at optimization algorithms in neural networks. So again, there are multiple like activation functions. We'll look at each of them. There is also I think they'll also give explanation on which one to be used when, kind of stuff. And this graph is pretty nice. So if all of these optimizers, if they start at a certain point like this, then how do they behave is what they're talking about. So let's observe one at a time. SGB is okay. There is no other color red, so this is red color. So if you look at it, um, SGB is actually coming from here to here, and it is stopping there. Okay, it is not going down. Whereas momentum, which is green in color, I'm not sure, it doesn't show here. So because the green line is not coming here, I'm assuming the green is also being stuck here, momentum. So but whereas nag, adagrad, Ada delta, and RMS prop. All of this, if you look at it, all these colors, if you observe, all these four colors are actually coming this way. Okay, one, two, three, four. Four colors are coming this way. I'm not sure if the green is coming or not, but we'll find out if the green will come or not. Okay, I think green is also coming this way. So get it. And then we have a concept of loss. Neural networks minimize it because of optimization. So, such as weights and learning rate to reduce the losses, optimizers are used to solve optimization problems by minimizing the function. So, how do optimizers are useful? A hiker trying to get down a mountain with a banana. Okay, okay. He's explaining gradient descent, which is okay. So, it is GD is gradient descent, as GD is stochastic gradient descent, and MBSGD is mini batch stochastic gradient descent. SGD with momentum. So that is the momentum here. Momentum is SGD with momentum, and Nestro accelerator gradient NAG. This I have not seen. Adaptive gradient ADA grad is this is famous. ADA delta, that's also famous. RMS prop is also famous, and then Adam is the most famous one and most used one. Each one of them, if you see, gradient descent is an optimization algorithm that's used for training a machine learning model. So this you gradient descent we have already studied. This the one which we have looked at in linear regression. The same gradient descent is being used here. um, this is one, a minus theta j minus alpha into derivative of cost by theta j. So it will come like this. This is gradient descent. This is all linear regression, same. Means how much the output of a function changes if you change the inputs a little bit. Okay, now importance of learning rate. Yeah, that's okay. Mm, Fine. This is learning rate, smaller learning rate, smaller steps, bigger learning rate, bigger steps, and bigger. So if you have smaller, it will take more time. Bigger learning rate, you might not reach the local optimal. So you should take an ideal value. How do you pick up an ideal learning rate? That's a different story. We'll get to it later on if possible. Um, Advantages are for gradient easy computation, easy to minimize, easy to understand. May trap at local minima. That's correct. So what happens is in here, what's happening? It will. So let's say this is one, this is two, this is three. This is maximum. Uh, Maximum max are the best minimal value, but gradient descent at times, if it is this is closure or this is closure, it might go here basing on the starting point where you go. So that's a disadvantage that to saying it might not be. So now let's go to stochastic gradient descent. So we understood disadvantages is may trap at local optima. Weights also change after calculating the gradients on the whole data set. So if the data set is too large, then this may take years to converge to minima. Requires large memory to calculate the gradient of the whole data set. Okay, so it takes some time. That's the whole summary. The compute is high, complexity is minimal, but the compute is high. The time is high. The stochastic gradient descent algorithm is an extension of gradient descent and overcomes some of the disadvantages of GD gradient descent. Lot of memory load in SGD algorithm derivative is computed taking one point at a time. So what they do, the input points, they don't go with all the points. They'll take one point. SGD performs a parameter update for each training example xi and label yi. So the calculation he says instead of taking all the x parameters, doing the whole math, he takes one x parameter. So He takes one x parameter and y parameter, and then he'll calculate it, and then he'll repeat that process. So to faster, we can take a gradient descent step for each training example. So for each training example, he will take a step. So it might not be a proper gradient descent because the cost is calculated for overall, correct? But here, what you're doing, the gradient descent, you're doing it for each example separately. So what happens? It might not actually result in reducing your cost, um, because you're not looking at the influence of the overall point. So what happens? You need to this, but as you calculate all the points, you will end up in gradient descent only. But to make your calculation easier, he's doing it. But the problem with this is, I think he'll give it in disadvantages. Um, the time required to complete one epoch is large compared to gradient descent algorithm, because you calculate for each example, and to complete all the examples it will take time, right? So the compute requirement could be minimal, but the time is more than GD. Again, SGD is needing more time than GD, but the compute math calculation is easier, and the time it takes to converge, that's what I was saying, right? It will take is, but still, and we don't solve that problem, saying still this can get and go and get stuck at a minimal local optimum. So for that, they came up with MBSGD, that is mini batch stochastic gradient descent. So instead of taking one example at a time, what he takes does is mini batches, nothing but he takes a group of values. So he divides the uh, whole data set into smaller pieces, and for each smaller piece, for each batch, he'll take the cost, and then he'll do a derivative, blah blah blah, and then he'll do it. Is the batch of training example. So for each batch, he'll separately calculate everything. So disadvantages here is, update of MBSGD is much noisy compared to the update of GD algorithm. Take a longer time to converge than the GD algorithm, right? May get stuck at local. So still the local optimal problem is being carried across all the gradient descents. It is not being solved anywhere. Stochastic gradient descent, and okay, this is now new one. He says SGD with momentum. So a major disadvantage of MBSGD is the updates of the weights are very noisy. SGD with momentum overcomes this disadvantage by denoising the gradients. Updates of weight are dependent on noisy derivative, and if we somehow denoise the derivatives, then converging time will decrease. The idea is to denoise derivative using exponential weighting average, that is to give more weightage to recent updates compared to the previous update. Okay, to accelerate the convergence. Okay, this is if you look at it, he's adding an additional term to this particular this thing, so that the now the weights are updated as v is equal to theta minus vt. So previously it used to be theta minus alpha into alpha of j of theta by derivative of theta, but instead we are actually doing weighted average of the previous values, and then we are doing we are creating a we are reducing the noise or something like that. But again, let's look at then GD has all these advantages, as in the CD converges faster than GD algorithm. We need to compute one more variable for each update. Yeah. So Nesterov accelerated gradient. I think this is just optimization on top of the SGD with momentum. In the case of SGD momentum, the momentum and gradient are computed on previous updated weights. It's okay. I'll skip that. Okay, let's talk of adaptive gradient descent, ADAGRAD. Algorithms, the learning rate remains constant. So the key idea of ADAGRAD is to have an adaptive learning rate for, yeah, so adaptive learning. So the problem is if you have a higher learning rate or a lower learning rate, what is happening? The the learning rate is either giving taking big steps or it says very small steps to reach local optimum. So adaptive gradient descent, I don't know why I forget this concept every time, is something where it actually takes a learning rate relative to the starting of the gradient to going down. So initially what will happen, the learning rate will be higher, so the steps will be bigger. But as you can see, basing on the way the cost is varying, the learning rate also varies in similar fashion. So the steps will get reduced. So once you start from a higher ground, the steps will be bigger, and I think he'll show a graph below, and it will change basing on okay, so he says GTII. What is GTII here? Change in cost. So change in cost is what is GTII. So change in cost will be considered as your learning rate will actually get affected by change in uh, the way the cost is changing. Number of iterations becomes very large, learning rate decreases to a very small number, which leads to a slow convergence. So what happens is from the top it will go fast, but as it goes closer to the output, it'll become slower. No need to update the learning rate manually as it changes adaptively with iterations. Okay. Under delta. So the problem with the previous algorithm under delta was learning rate becomes very small with a large number of iterations, which leads to a slow convergence. To avoid this, under delta algorithm has an idea to take an exponential decay average. So okay. The way you reduce the learning rate, they are actually instead of doing basing on learning rate by the difference in cost and stuff, they're going for exponential value so that the um, learning rate doesn't get reduced. Uh, the rate of reduction in learning rate is actually proportional to the square of the change in the cost. So that's how they keep moving the learning rate so that it is not uh, it doesn't get too low, the steps doesn't get too small during convergence, it'll become meaningful. Yeah, so ada delta gt plus e, replacing the diagonal matrix gt with the decaying average or past squared gradients, eg square of t. He says here um, t plus 1 minus gt is as a fact in fact is identical to the first update vector of ada delta that we derived above. Ms. Pop as well divides the learning rate by an exponential decaying average of the squared gradients. So they take a certain amount of the previous. plus the certain amount of gradient descent of the derivative of the present one. Usually lambda is set to 0.9 relating SGD in terms of the parameter update vector. Okay. And coming to RMS prop, what does it say? Again 0.9, 0.1. Everything is same. Divides the learning rate by an exponential decaying average of squared gradients. Hinton suggests y to be 0.9. What is the difference? I don't. The difference between RMS prop and delta have both been developed independently around the same time, stemming from the need to resolve ADA grids, radically diminishing learning rates. ADAM, adaptive momentum estimation. Adaptive momentum estimation. Okay, ADAM has made the combination of RMS prop and stochastic gradient descent with momentum. Okay. The ADAM that we're looking at, it is again not. It's not being done at batch. See, stochastic is okay. I'm lost with things. Stochastic is individual, each term, right? Stochastic is this is gradient descent. Stochastic is each term, and mini batch MBSGD is mini batch, and SGD with momentum MBSGD is. So Adam, we should see, is it mini batch or is it each example? Adam computes adaptive learning rates for each parameter in addition to storing an exponential decaying average of the past square gradients under delta and RMS prop. Adam also keeps an exponential decaying average of exponential decaying average of past squared gradients, average of past gradients. So VT is exponential decaying average of past square gradients. MT is gradient. So like gradient square and gradients both are being included. So if you look at it, the ADA um, ADA grad was doing gradients. ADA delta was doing ADA delta was doing gradient square, and Adam is doing both. So MT is Z, and this is Z square. Okay. All of them, if they're starting by number of iterations, if you go, the training cost for highest is Adagrad. It's going higher here as the number of iterations for Adagrad is higher. RMS prop is second. Ada delta is third. SGD Nestro is third, fourth, and Adam is fifth. So Adam is the best among all these. They're the best algorithm amongst all. So I don't understand if Adam is already the best. Why do we need to use the remaining? Okay, so these are all the optimization techniques. I think this is how they have evaluated. But let's ask a question. That's a good question to ask. Do we use while Adam is the best optimizer for neural networks. Other optimizers in any other scenario is popular and effective optimizers for training networks. There are indeed scenarios where other optimizers are preferred. That's a good question to ask. Like we can say, but as per that graph, actually Adam is less. Compare Adam to other optimizers with respect to cost, compute, and convergence time. In tabular format between Adam and GB, SGB, MB, SGB, Adam, Adam grad, Adam delta. Where's the comparison? Okay. Add columns as cost, compute, and time. So let's look at it. Adam delta, moderate, 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 moderate. So this guy is giving everything is moderate. Okay. Cost wise, it still says LB is low. Time wise, that is low. Compute wise, everything is high. Doesn't matter. Because even though you do with a batch or individual term, your overall compute will be the same. Only thing is you can do it parallel and then reduce some time and all that stuff, but your overall compute will be almost the same, right? So if you want to reduce cost, then you need to use other optimizers. Otherwise, time wise, it is Adam is lowest time wise with respect to all of them. Compute wise, it is high. Uh, if you go with mini batch and stuff, they're a little better. So it's more compute and cost. And if time is important, go with Adam. If you want to save cost, then go with gradient descent in boosting. In boosting, yeah, in descent, man. Oh, he is giving gradient boosting. But anyways, doesn't matter. Is it SGB or SGD? SGD only. Very clear. SGD. I think because of my input, it got confused. Okay, optimization also we have seen. Not sure how much time it took somewhere. Oh, it's already 1 hour. So regularization is very small concept. Let's look at regularization tomorrow then. It's long. It's taken a long time today, but we have covered optimization. We have looked at equations, which is nice. We looked at specific equation, but I think you guys could understand the sigmoid and sigmoid tan h and all that stuff, those are okay. We can look at it like that. But if you go to relu or something like that, which is more like leaky relu or relu kind of stuff, so then what happens, it is 0 comma, then you can't literally put it into a mathematical equation. um, Matter of fact, you can represent anything in a mathematical equation based on value, you change it, right? So that can be done. But it's okay. But you understand the gist of it. So it's a multi-layer um, ca- equation formation, which in turn makes it a complex equation. Neural networks in turn keeps a complex equation, and the specific complex equation, you can always solve any problem. That's the whole that we have understood in linear regression itself. So we can actually do overfitting for any of the given data sets. The compute will be high, and the cost to compute and time will be very high. So neural networks is also in turn putting up a complex algorithm to solve that problem, which we already know that complex algorithms will solve such a kind of problem. But neural networks makes it easy. It at least appears that it is very easy to solve that complex equation by breaking it down into smaller pieces and computing it. And the imagination is that the brain also, using so many neurons interconnected, it does the same thing. Instead of doing the whole thing, it breaks down into smaller pieces and then acts. Okay, thanks guys, and stream end 8:30.